Hello all. So we'll continue with the moving charges in magnetism. So we have to start with question number 4.21. Okay, so please open your NCERT textbooks and you will get the question right there. So question number 4.21 is a straight horizontal conducting rod of length 0.45 meter. So you are having a rod whose length is 0.45 meter, and this is having a mass of 60 gram. This is having a mass of 60 grams. So the length is equal to 0.45 and mass is equal to 60 gram, is suspended by two vertical wires at its ends. So this is suspended by two vertical wires. Okay. Now what is the question? What is the magnitude? And in this wire you are having a current of 5 ampere. Okay, so the current in the wire is 5 ampere. You are having two wires which are holding this rod. So the question is, there are two parts in this question. The first question is that they are asking what should be the magnetic field, what should be the magnetic field B for the tension in the wire to be 0. Okay, so here the wire has tension T. So we want to set up a magnetic field in such a way that the tension in the wires should be equal to 0. Now, because you have connected these, suspended this wire here like this, you will have the tension T here. These two are same wires, same length, same material. So both will have the same tension T. Okay, now what is the force that is acting, that is creating this tension? So we have the mg force of the wire, mg weight of the wire, that is acting downward direction, that is creating the tension here. So in case if the magnetic field is set up in such a way that you have a force in the upward direction, okay, then the net force on the wire, net force on these wires will be equal to 0, and hence the tension acting on them will be equal to 0. So basically the Lorentz force that is acting on this wire must be equal to BIL. Okay, it's actually BIL sine theta, but since current and length is 90 degrees, we will take sine 90 as 1. So mg is the force acting downwards. You need a force acting in the upward direction which will be equal to mg, so that the tension in this wire will be equal to 0. Okay, so we have our values. So L is equal to 0.45 meter and M is equal to 60 gram. Okay, so using those inputs, we will find out what is the magnetic field B. Okay, so B is equal to, first I'll write here BIL, that is the force, should be equal to mg. Only then the tension will be equal to 0. Okay, then what is B equal to from this? It is equal to mg divided by I into L. So M is 60 into 10 power minus 3 into 10 meter per second square, divided by current is 5 ampere and the length is 0.45. Yes, so if we solve this, you will be getting the magnetic field as, so let us see what's the answer, 0.26 Tesla. Okay, so you can do the calculations on your own. Okay, so if the magnetic field is 0.26 Tesla, then the tension in the wire will be 0. Now, what will be the direction of the magnetic field? So, we have force acting in the upward direction and current is acting in this direction. So, let us use our left hand rule, Fleming's left hand rule, to find out the direction of the magnetic field. So, the force is pointed by which finger? The force is pointed by the thumb finger, the magnetic field is pointed by the index finger, and the current is pointed by the middle finger. So we will place our current like this. Okay, so it is from left to right, so the current is in this direction, and the force, the thumb acts as the force. So you will be pointing your fingers like this. So where is my index finger pointing? My index finger is pointing into the field of, into the board, plane of the board, okay, or into the plane of paper as in your case. Okay, so therefore the magnetic field will be acting into the plane of paper. Okay, only in that case you will be getting a force in the upward direction. So that is the first half of this question. So we will see what is the second half now. The second half of the question is that if the direction of the field is reversed, what will be the tension in the wire? Okay, so when we reverse the direction of the field, how will we place our Fleming's left hand? So the field is coming outwards, okay, and the current is going inwards. So now the force will be acting in the downward direction. So if the force is going to act in the downward direction, that means the tension will be doubled, okay, and that force was equal to, magnitude wise it is equal to mg, that we have already, from that only we found the magnetic field, isn't it? So tension will be 2 times the weight of the wire, okay, which is equal to 2 into 60 grams, that is 60 into 10 power minus 3 into gravity, that is 10 meter per second square. So the answer is 12 into 1200 into 10 power minus 3, which is equal to 1.2 Newton. So that will be your answer. That's it. The next question, 4.22, is the wires which connect the battery of an automobile to its starting motor carrying a current of 300 ampere for a short time. Yes. Is what is the force per unit length between the wires if they are 70 centimeter long? If they are 70 centimeter long, so centimeter, I will straight away convert it into units, SI units. Okay, 70 centimeter long and 1.5 centimeter apart. So the distance between them is 1.5 centimeter. So 10 power minus 2 meter. And they are asking, is the force attractive or repulsive? So first of all, they are asking what is the force per unit length? Okay, small f, that is nothing but the capital F by L. And they are also asking what is the what is that direction, that is whether the force is attractive or repulsive. So the first thing what we will do is we will find out the force per unit length. So small f is equal to mu naught into I1 into I2 divided by 2 pi r. So this is a formula for force per unit length of two wires carrying current kept close to each other at a distance of r. So this, if we substitute, we will be getting 4 pi into 10 power minus 7 into, now both the wires are carrying the same current. So that will be 300 into 300 divided by 2 pi r. So 2 into pi into, the distance of separation is 1.5 into 10 power minus 2 meter. So if we cancel this 2 times and 1.5 will go 2 times, correct. So I'll write 200, 2000 times it will go. Okay, this is 3 by 2. So to avoid any confusion, sorry for my weak mathematical skills, and into 2, I'll multiply that in the numerator. So what have I left with? So 2 into 2, 4 into 3, 12. Okay, so that is equal to 12 into 10 power minus 7 and 10 power 4, 10 power minus 3. This goes to the numerator, 10 power plus 2, so that is 10 power minus 1 Newton. So, or I can write 1.2 Newton. So, this will be the force per unit length between the two wires. Now, they are asking whether this will be attractive or repulsive. And this is Newton per meter because this is force per unit length, isn't it? So, it is Newton per meter. They are asking whether it will be attractive or repulsive. Now, the battery, the wire from the battery is connected to the starting motor. Okay, so you're having some motor. Now if the if it is connected from battery, obviously it will be a positive and a negative terminal, and the current will be acting in opposite directions in both. Yes or no? The current will be acting opposite in both the wires. So whenever we have two wires of opposite current directions, that means the force will be repulsive. So F is repulsive because the current is in opposite direction between the not between, opposite direction in the wires. So that will be your answer. Okay. So starting with the next question, 4.23, a uniform magnetic field of 1.5 Tesla exists in a cylindrical region of radius 10 centimeter. Okay, now we have to very carefully understand this question. Okay, so there is a cylindrical region, okay, in which you are having the magnetic field set up, okay, from the east to west direction. Okay, so I'll write the direction of the magnetic field is cylindrical and it is along the east to west direction. Now you have a wire carrying a current of 7 ampere in the north to south direction that passes through this region. Okay, so we will consider a wire is there. Okay, so let us consider a wire here. Now this wire is passing through this east to west magnetic field from north to south direction. Okay, so from this point to this point will be the length of the wire that is exposed to this magnetic field. Yes, so the first part of the question is you have to find out what will be the force acting on the wire due to this magnetic field. Now they have given the magnetic field is equal to 1.5 Tesla. Okay, and the length of the wire will be equal to what? The radius is given as, radius of the cylindrical conductor is given as 10 centimeter. So 10 into 10 power minus 2 meter. All right. Therefore, the length of the wire that is exposed to this magnetic field will be equal to 2R. Okay, L is equal to 2R in the first case. Clear? Now, what is the current carried in the wire? So that is I is equal to 7 ampere. We have to find out the force acting on this. Now what will be the angle between the magnetic field and the length of the wire? So that angle is 90 degree. Therefore we will write BIL sine theta, and here BIL sine theta is 90 degree. Okay, so instead of BIL I'll also substitute the values. So I have 1.5 into 7 into what is the length? It is equal to 20 into 10 to the power minus 2 meter into sine 90 degree. So the answer for this will be equal to 14. 1.5 into, sorry, 72 is 14 and that into 1.5 will give me totally 2.1 Newton. Okay, 2.1 Newton. So this is the force acting on the wire, and which direction will be the force? So we will use a Fleming's left hand rule. Yes, and we will apply the magnetic field. So magnetic field is which finger? It is the index finger. Magnetic field is acting from east to west, and the north to south is the current. So current is given by the middle finger. So north to south is the current. East to west is the magnetic field. North to south is the current. So you can see my thumb is pointing into the plane of paper. Okay. So the force acting on this conductor will be, on this wire will be into the plane of paper. So that will be the answer for this. So I can write here the force will act into the plane of paper. Okay, so that is the first half of the question. Now in the second half of the question, yes, B section, they are giving that the wire is tilted, okay, either to northeast or to northwest. Okay, it is tilted to northeast or northwest direction. So you can write, let us take this direction. Okay, now we know that the current is flowing like this, okay, in this angle. Okay, so the angle between the magnetic field and the length of the wire will be taken as theta. This is theta for us. Okay, and if this is theta, this angle is also theta. Now, what is this point? So this is A dash and B dash. Let us name this as AB. Now, the length that is exposed in the magnetic field is changed. Okay, the length of the wire that is exposed in the magnetic field is changed. And what will be this new length? So the new length is A dash B dash. Okay, that is equal to L dash. All right, and AB is equal to L. So if we consider this whole triangle, yes, we are considering this whole triangle. This is L and this is theta. So what will be the hypotenuse? So if we take sine theta, yes, we will get opposite by hypotenuse, which is equal to L by L dash. So I'll write this as L by L dash. So what is L dash from this? So L dash is equal to L by sine theta. Yes, so we got our L. Now we have to find out the new force. So that will be B into I into L dash. Okay, so what is B? And here we do not have that sine 90. Okay, we have sine theta here because the angle is not 90 degree. So this will be the entire equation, and we have B into I into, what is L dash? L dash is L by sine theta, and what is this? Sine theta. So this will get cancelled. Now I did not tell you why we are taking this length. So we have to take the length that is exposed in the magnetic field direction only. Okay, so in the direction of the magnetic field, how much length will be effectively given? So the effective length is this much only. The cos component of this length will not be affected by the magnetic field. It will not create any force will not be created on that. Only the length which will be what do you say, perpendicular to the magnetic field will be applied here. So even by theoretically we can just say without calculating also we can say that the force is going to be same in both the cases. Okay, because even though we rotate the wire, the angle, the length that it is going to appear is going to be the same. Okay, the length, the vertical component of the length is going to be the same, and that component only is going to get affected in the magnetic field. So once again you're getting BIL, which is equal to 2.1 Newton, and this force is also acting into the plane of paper. Okay, now here the C part, you're having another question, that is let me erase the board. So the C part of the question is that you have to find out what will be the force acting on the wire if the wire is lowered, okay, by 6 centimeters. Now the word lowered here is slightly confusing. Okay, what they're actually trying to say is, if you look at this setup, okay, in top view, okay, if I look it from this side or this side, this will be the diagram. Okay, so this is a cylinder into the paper. Okay, and this is the coil that is passing through the cylinder. Yes, this is the coil that is passing through the cylinder. Now this coil you are lowering. Okay, that means in this diagram you are bringing it forward. Okay, so a diagram is slightly different, but the concept is that you are trying to lower it by 6 centimeter. Okay, you're trying to lower it by 6 centimeter. That means the new wire will be occupying only this much length. Okay, so we have to just do geometry, and we need to find out what will be the length of this wire, and then all the other things are same. So in this case also, the force acting on the wire is going to be 90 degrees only. I mean, sorry, the length of the wire and the magnetic field is going to be 90 degrees, because here if you consider this side to be the north and south, that means the east and west. East is inside, the magnetic field is coming towards you. Okay, so that is east is behind the paper and west is towards you, so it is coming out of the paper like that. Okay, so the length and the magnetic field are 90 degrees in this case also, so theta will be 90 degree. Now what we need to find out is the length of the wire. Okay, so if this height is going to be 6 centimeters, okay, so let me write it down. So the height is 6 centimeter, and what is this length? This length will be the radius, that is 10 centimeter. So this length you can easily calculate using your Pythagoras. So you will get 10 square minus 6 square. So that is 100 minus 36, which is equal to 64, and square root of 64 is equal to 8 centimeter. So the total length of the wire will be 16 centimeters. Okay, and that 16 centimeters you will be applying in the formula BIL. Okay, so in this case, B is 1.5 Tesla into 7 into the length here is 16 into 10 power minus 2 meter, and here sine theta is 90, so sine theta is equal to 1. So the answer for this will be 1.68 Newton. Okay, so the answer for this is 1.68 Newton. So this will be the force acting on the wire, and this force, shall we see the direction for this force is how it will be acting. So in this type of setup, if you fix your north to south, okay, that is the current direction. So this will be like this, and your index finger will be pointing towards you. Okay, so where is the force acting? It is acting in the downward direction. Okay, see in the previous case we had totally twisted this diagram. Okay, so according to our diagram we had set up. Now if you want to if you don't want to this confusion, what you can do is you can fix the axis. Okay, you can say x axis, y axis and z axis, like that you can fix the axis, so that in all the three cases you don't change the axis, and in that case you will be getting the same direction for all the three cases. Now for the first two cases I chose this diagram, but for the third case I've chosen this diagram. But the ideology is that the force is acting in the same way only in all the three cases. Okay, the direction of force is not changing. Okay, so you should be very careful how you define the direction. Okay, so it should be proportional to your diagram. Okay, so it should be satisfying your diagram. That is the main thing. Yes. The next question, 4.24, it's quite an interesting conceptual question. Okay, so they have given the uniform magnetic field of 300 Gauss, 3000 Gauss. Yes, it is acting along the positive Z direction. Okay, so that means it is acting along the K direction. Okay, K cap vector it is acting. Now the question is that, and 5 centimeter, sorry, a rectangular loop of sides 10 centimeter and 5 centimeter is there. Okay, so there are different positions given for the rectangular loop. Okay, so the dimensions of the rectangular loop are 5 centimeter and 10 centimeter. Now what are they asking us? It is carrying a current of 12 ampere. Okay, so it carries a current of 12 ampere and its length is 10 centimeter and breadth is 5 centimeter. All right. Now they are asking what is the torque on the loop in different cases as shown in the figure, and what is the force on each case, which case corresponds to stable equilibrium. All right. So we will see here, in all the cases the common thing that is going to be is the magnetic moment. Okay, the what do you call that, magnitude of the magnetic moment is going to be same. What is the magnitude of magnetic moment? It is current into area. Okay, it is current into area. So I will just calculate quickly what is the value for this. So this is 12 into area is 10 into 5, 10 power minus 4. So that is 50 into 10 power minus 4. And the answer is equal to 0.06 sorry, 0.06 ampere meter square. So the value of M. Okay, so I'll write it here. I don't want to disturb this diagram. Okay, so B magnetic field is given as 3000 Gauss, isn't it? So that means 3000 into 10 power minus 4 Tesla, that is equal to 0.3 K cap Tesla. Okay, so that is the magnetic field. So I'll write the value alone. B is equal to 0.3 K cap Tesla. Okay, so I'll erase this off. We don't need that. Then magnetic moment M is equal to 0.06 ampere meter per minus 2. This is a vector quantity, but I'll write only the magnitude. You will know why. Okay, and now we will get into the question. Now they're asking us to find out the torque in each case. Now you know very well torque is equal to M vector cross B vector. Okay, so in each case our duty is just to find out what is the direction of M vector. Okay, so the direction of M vector in the first case will be, how to find out the direction of the magnetic moment. So you have to curl your fingers. You have to use your right hand thumb rule. You will curl the fingers along the direction of the current, and the thumb will be the direction of the magnetic moment. Okay, so in this case it is going anti-clockwise. So it is perpendicular to the YZ plane, which means it is x-axis. Okay, so in this case the magnetic moment vector is 0.06 into I cap. Okay, and in this case the magnetic moment will be, let us do it. So it is along this direction. Okay, and once again the magnetic moment is along the positive x-axis, that is 0.06 into I cap. Then what about in this case? So here your current is going in the clockwise direction, so it will be like this. So that means the magnetic moment will be perpendicular to the xz plane. So that will be M vector is equal to minus 0.06 into J cap. It will be along the negative y direction. Then in this case we will wait, okay, for this case. And what about this one? So the magnetic moment here will be along So this is in the clockwise, it will be along the positive z axis. So you will have 0.06 into k cap, and here the magnetic moment is clockwise, so it will be along the negative z axis. So it will be minus 0.06 into k cap. Okay, so we will find out the torque in each case. Yes, so the torque here is m vector cross b vector. Okay, so what is the magnitude for this? So 0.06 into b vector. What is b vector equal to? It is equal to 0.3, okay, multiplied by the direction. Now how to write the direction? So this is I cap cross k cap. Okay, so what is I cross k? So I is x-axis, I cross k means it will be, you have to fold the fingers like this. Okay, so you have to keep the fingers like this, and then you have to cross to the x-axis. Okay, so basically it is like this. Okay, x-axis is towards you, so you are crossing towards the z-axis. So x to z, so it is along the negative is y-axis. So that will be minus j cap. The direction is equal to minus j cap. So what is 0.6 into 0.06 into zero point 0.3? It will be equal to 18 into 10 to the power of minus 3 minus j cap. Okay, so that is minus 18 into 10 power minus 3 j cap. Okay, so similarly we will do it for all the cases. So here you are having torque is equal to, once again you will get the value as 18 into 10 power minus 3 only, but the direction alone will be differing. So the direction will be equal to, this is I cross k. Okay, so this, in this case also it is going to be minus j. Okay, then what about here? So here you will be having the minus j cross k. Okay, so what is j cross k first of all? So j is this cross k. Okay, so it is along the positive x-axis. So j cross k is positive x. So since we have a minus sign, so it will be negative x-axis. So here torque is equal to minus 18 into 10 power minus 3 into I cap. That is along the negative x-axis. Yes, and here we will wait. So what about this one? So here you are having the torque is, this is k. Here we have to do k cross k. We will do k cross k. Okay, so what is k cross k? K cross k is equal to 0. Okay, so here in this case the torque is equal to 0, and in this case also you have minus k cross k, so that is also equal to 0. Okay, now what about this case? So this is similar to the third case, okay, except for the fact that you are tilting this axis. Okay, so basically this coil is like this along the xz plane, and you have shifted its angle. Okay, it's like opening a door. Okay, so you have shifted its angle up to 30 degrees from the y-axis. So what will be its angle from the x-axis? It will be equal to 60 degree. Okay, now that means the torque here, it is acting along the negative x-axis, isn't it? So the, imagine the torque is also moving as you open this coil. Okay, so you're basically opening the coil like this. Okay, so the torque will be acting in such a way that it is at negative 60 degrees from the x-axis. Okay, so it was actually acting in this direction. Okay, along the negative x-axis, the torque. Okay, so and because you opened it, it is tilting towards this side. Okay, so it will make, from the x-axis it is going to make an angle of 240 degrees, and or you can say minus 60 degrees. So that will be the value of torque. Okay, so we are not going to mention the vector form like that, rectangular components. We are going to give this answer as magnitude and direction separately. Okay, so the direction of the torque is 240 degrees from the positive x-axis. So from this point, okay, you have to go all the way along this. Okay, so if you are rotating along 60 degrees, then you have to take this angle. So this will be 240 degrees, or you can say this degree to be minus 60. Okay, so that will be the answer. Then one more question they had asked, whether which one is stable and unstable equilibrium. Okay, so this case, okay, where the torque is 0 means it is in equilibrium, and this one is also in equilibrium. Now which one is stable and which one is unstable? So if this particular coil is tilted from its axis, the torque will act in such a way that it will again bring it to the same position. Okay, but in this case, if you slightly tilt it, it will rotate completely 180-degree, and then it will again come back to the z direction. Okay, so it will rotate its angle by 180. So this one is unstable equilibrium. Okay, because this is anti-parallel, the magnetic moment is anti-parallel to that, and here the equilibrium is stable. Okay, so that will be the answer. That is how you answer this question. The next question, 4.25, is that a circular coil of 20 turns, okay, is placed, and radius 10 centimeter is placed in a uniform magnetic field of 0.10 Tesla normal to the plane of the coil. Okay, so it is placed normal to the plane of the coil, and if the current in the coil is 5 ampere, what is the torque, the force on the coil, and the average force on each electron? And it is given that the cross-sectional area of the wire used is 10 power minus 5. This radius is the radius of the coil. Okay, this is the radius, this is the area of the wire. Okay, cross-section area of the wire. And the number electron density is given as 10 power 29 meter minus 3. Yes, so they're asking what is the torque acting on the coil. Now you know very well torque is equal to m cross b. Okay, m vector cross b vector. Now if the coil, okay, is perpendicular to the magnetic field, okay, that means the magnetic moment is also will be parallel to the magnetic field. Okay, so basically the coil is like this, the magnetic field is in this direction, so the magnetic moment is also in the same direction, so both are along the same direction. So for parallel vectors, the cross product is equal to 0. Okay, then the B portion, they are asking what is the force acting on the coil. So the force acting on the coil will be in such a way that the forces will be equal and opposite in direction along every diametrically opposite element. Okay, so for every diametrically opposite element, the force acting on it will be equal and opposite. So it will cancel everything. Therefore, the net force acting on the coil will be equal to 0. And the third thing is, they're asking what is the force on each electron. So the force on each electron will be equal to BeV, that is BQV. Okay, and BQV can be equated as, or I can write current as I is equal to NEAV. Yes, so in this I can replace E into V by I by NA. So I can write B into I divided by small n into capital A. Yes, so now we will substitute all the equations. So you will have, sorry, all the values. So B is 0.10 into current is equal to 5 ampere divided by number density is 10 power 29 into area, cross-sectional area will be 10 power minus 5. So the answer for this is, this can be written as 10 power minus 1. Okay, so the answer for this will be 5 into 10 to the power of minus 25 Newton. So that will be the force acting on each electron. Okay, 5 into 10 power minus 25. So that will be your answer. The next question is, a solenoid 60 centimeter long and of radius 4 centimeter has 3 layers of windings of 300 turns each. So they're describing the solenoid, and a 2 centimeter long wire is kept inside the solenoid, okay, whose weight is 2.5 grams. So there is a 2 centimeter wire whose weight is 2.5 gram. Okay, and this wire is kept in such a way that it is perpendicular to the axis of the solenoid. Now the axis of the solenoid is this, so it will be kept perpendicular, as in it is into the paper, because they have given that both the field and the wire is in the horizontal plane. Okay, so this is your horizontal plane. Imagine this as xy plane. It is passing like this. Okay, so the field is along this direction, for example, then the current is along this direction. Okay, so the wire is kept into the paper. Now they are asking what will be the current, what should be the current such that the the wire does not fall. Okay, meaning its weight is balanced by the Lorentz force. Okay, so that is what they are asking. So we have to balance the weight by the Lorentz force. So for that, what is the current that I should supply? Okay, so if this B is a magnetic field, yes, and here they have not given in which direction the current is flowing in the wire. So we will not worry about the direction. We will assume, and for the magnetic field also they have not given the direction. So only magnitude wise we are going to solve this question. Okay, so we will see first what is the magnitude of the magnetic field. So to find that, first the answer for this will be mu naught into n into I. So the small n we have to calculate. So what is the value of small n? Small n is total number of turns, okay, divided by length of solenoid. Okay, so the total number of turns is equal to three layers of windings are there and you have 300 turns. Okay, divided by length of the solenoid. What is the length of the solenoid? It's given as 60 centimeter. Okay, so 60 into 10 to the power of minus 2. Therefore, the number of turns is equal to 1500 turns per meter. Turns per meter. Alright. And the magnetic field is mu naught into n into I. So 4 pi into 10 power minus 7 into n is 1500 into I. Okay, so that will be your thing. So this 4 into 50 is 60. Yes, so you will have in the end 6 pi into 10 power minus 4 into I Tesla. Okay, so we don't know what is I. So the force that should balance the weight of the object should be equal to F is equal to BIL, isn't it? So here your B is 6 pi into 10 to the power minus 4 and I is already there. Okay, so we will just not write that I, repeat that I again. So this, yes, and into the length. Now what is the length of the wire? The length of the wire is given or not? 2 centimeter long wire. Okay, so the length of the wire is 2 into 10 power minus 2. So I'll put it as L dash because the length of the wire. So this should be equal to the weight of the wire. So that is equal to, what is that? 2.5 grams. So 10 power minus 3 into 10, that is the acceleration due to gravity. So this should be equal to 6 pi into 10 power minus 4 into 2 into 10 power minus 2 into I. So I is equal to this divided by this. So the final answer for I current is equal to 108.3 ampere. Okay, so this answer is 108.3. Okay, so this is how you will solve this question. Okay, so this current is the current of the wire inside this. Okay, so this will be, sorry, not this one, this I dash. Okay, so instead of I dash, I will multiply 6 ampere current. Okay, so one more 6 will be multiplied here. And that answer is only is 108 point. Okay, so this force, okay, is acting on this wire, isn't it? So this current they are given. This is I is equal to 6 ampere. That is given. The current in the solenoid only we have to calculate. Okay, so that one small change. The answer is same. Okay, so since I've seen the answer in the book, I've written it directly. Yes, so that will be your answer. Okay. The next question is, a galvanometer coil has a resistance of 12 ohm. So the resistance of the galvanometer is 12 ohm and this shows a full scale deflection for a current of 3 milliampere. Now whenever they say full scale deflection in the galvanometer, it means there is a galvanometer current. Okay. And we want to convert this galvanometer into a voltmeter, which will be ranging from 0 to 18 volt. Okay, so that means the maximum value of the voltage should be 18 volt. So we have to frame or we have to find out the resistance that will convert this galvanometer into voltmeter, and this resistance should be connected in series with the galvanometer, and that entire setup will be connected in parallel in whichever required circuit. Okay, so R is equal to V divided by Ig minus Rg. Okay, so this is the formula V by Ig minus Rg. So that V is equal to 18 divided by 3 into 10 power minus 3 and minus, what is the value for Rg? That is equal to 12 ohm. So the answer for this will be, that is, so here you will have 6, so 6000 minus 12. Okay, so that will be 5988 ohm. So that should be the resistance that is connected to this voltmeter that will galvanometer that will convert it into a voltmeter. The last question of this chapter 4.28 is given. A galvanometer has a resistance of 15 ohm. So the galvanometer resistance is 15 ohm and the meter shows full scale deflection for 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 ampere? So I is equal to the maximum current in the ammeter is 6 ampere. So you have to find out the value of shunt resistance. Okay, so that will convert the galvanometer into an ammeter. So shunt resistance should be connected in parallel with the galvanometer and that setup will be connected in series in the circuit. Okay, so S is equal to Ig divided by I minus Ig into the resistance of galvanometer. So simple. So Ig is equal to 4 into 10 power minus 3 divided by 6 minus 4 into 10 power minus 3. This into Rg, that is equal to 15. So once you calculate this, the value of shunt resistance is 0.010 milli ohm, and that is nothing but 10 into 10 power minus 3, sorry, 0.010 ohm, which is equal to 10 into 10 power minus 3 ohm, or you can say 10 milli ohm. So that is the value for the shunt resistance. Okay, so this you need to connect in parallel and the entire setup will be connected along with the galvanometer and the shunt will be connected in series in the circuit as an ammeter. Okay.